Okay, so we're going to do a little bit more work on the robot. So it's a hardware demo that we've done for years, and we really like it for a number of reasons. It's interesting mechanically. It's a robot, so generally people come up to speed very quickly on what's supposed to do and what's not supposed to do. It's interesting with the electric motors and the electronics, and of course the controls, and I'll add also the trajectory planning. All right. And one of the things we discovered as we ran this for the first time is that we actually had a problem. And at first we were annoyed, but then we kind of realized, oh, this is perfect from a presentation point of view, because it kind of reveals problems do occur and that a good fix can take place through a simulation-based method that's available with Simulink. We call it model-based design. And I think that the potential fixes, they're all right there, and you can kind of see it at this level. We could slow it down, right? And so in our trajectory plan, I provided I'll call it a timing parameter, which I call nominal transition time, right? And this is kind of like a kickoff video. So I'm going to do a bunch of videos that are kind of on this topic of the robot, and I might dedicate one for that approach of slowing it down. But for right now, let's just kind of, introduce kind of the various topics. And I'd say this idea of doing a quick fix is kind of the point, right? And so we're going to fix this. And I'd say the controller is pretty good, so I'm not going to go there. But I think that the true constraints on what this robot's capable of doing is what it is mechanically and what it is electrically, right? And mechanically, we kind of represent the whole thing with SimScape multi-body, where each part of the assembly is directly represented with its mass, inertia, and so forth. But the idea of going into a redesign, probably not our first choice because, again, expensive and time-consuming. And so the easy fixes, I think, are on the electrical side, right? And so in previous videos, I've just come in here and I said, well, let's make it 30 volts instead of 10 for our DC source. And from there, electric motors, kind of electrical things, they don't really care what they're initially connected to, other than that they might melt if you put too much voltage on it. But you'll see that part of my redesign of this demonstration was to come up with a parameterization that really kind of matches the way engineers really work. And you work with vendors and they provide catalogs. And based on things like nominal voltage and stall torque and no-load speed, you make your choices for motors. And, I decided to choose 30-volt motors, and therefore I think perhaps that is one way you might fix this. But I really do have an alternative. Again, I'm going to confirm. We're now going to run at 30 volts, which is my alternative motive. Let me hit spacebar right there. And you'll see that kind of the idea for motor selection is very contingent on the idea that you know how fast each motor is moving, and you know how much torque it's providing. So, let's unsuppress that. Right, and connect into this, and let's rerun it again. Okay. And so ran pretty close to real time, but in playback mode, I want to run it even faster because I want to cut to the chase. All right, so first of all, it goes through its trajectory perfectly. All right, I want to bring it to here. Now, this is the hardest part of the whole trajectory, is when the robotic arm brings the whole thing back to a vertical position. And very specifically, it's a motor that acts right here. And you can kind of see that that's all part of this thing called forearm, and we do call it the forearm motor. So it's finished the trajectory, and you see it comes up perfectly. All right, now probably the most realistic, I think, way of fixing this, because our motions are reasonable. It should, and you really do want these to move as fast as possible, is to kind of check these trajectories, and I'm going to specifically focus on the forearm. And you'll see speed in the upper panel, it's top speed at the beginning as well as top speed at the end, are a little bit over 1 radian per second. But at the end, it kind of has the highest torque too, and that's about 0.6, all right? Now this is still a little bit of, you know, well, I want to get it a little bit into motor selection right now. And so I want to go back in here. Okay, let's change our voltage back to 10 volts. All right, make this bigger. All right, and when we say 1 and 1, I'm going to play it a little bit safe, and so I'm going to redefine this with 10 volts, and I'm just make everything 10, 10, 10. All right, and yeah, again, I'm not sure why the inductance was this value, but it's usually a parameter from motor catalogs for me. And I think 1 to E minus 4 perhaps is pretty good. I'm going to just kind of put in a simple number like that and keep everything simple. And then let's kind of set it up so all the motors are being replaced. From a production point of view, that might be easier. You might get a better deal if you're using the same motor for each axis. Let's get these down here too. Okay, and just to keep the video kind of quick, I'm going to do one additional thing, all right? And what I want to kind of get at, you know, is that these are all DC motors, and I guess I'll show it to you. It's all from Simscape Electrical. All right, and so here's our DC motor, and I'll keep it as simple as that. Here's kind of the basics of our control algorithm. It's a PI control. And what I want to do is show the alternative. All right. And actually, the best way to show this is the model first. All right, so here's an electric drive. Electric drive is a little bit more than just the PMSM, which we see here, and we know it's a PMSM because Simscape Electrical tells you so. But we also know PMSMs are typically three-phase voltage motors, and we're kind of seeing all the connections that we need there. But as an electric drive, it's not just the motor, it's the actual current controller, and they call it field-oriented control, and it's here where we do all the really interesting algebra, not algebra, trigonometry, quark transforms, all kinds of stuff like that. And again, kind of the key thing, and I love this really, it's kind of true for both DC motors as well as PMSMs, that the important input really is torque. You know, there, in a way, I like to say there's no such thing as position or velocity control. There's some loop, maybe with a PID controller, that takes position or velocity commands, compares to feedback, and identifies a torque. But generally, torque is a real variable that's going to be driving the overall system, right? And through this, we get the voltages, and that's the job of field-oriented control. It's to convert torques into voltages, right? So anyways, so we run this one, and we get what we expect for a PMSM. You know, and I've been doing this kind of stuff at MathWorks for a while, so I'm definitely become, oops, I want to click it here, familiar with this kind of, you know, idea. Let's make it even bigger, right? That there will be 3 voltage waveforms. They're all going to assume sinusoidal shapes as you get to a constant velocity on the shaft. And they're essentially going to be what I'd call 120 degrees out of phase with each other. But it's essentially balanced voltage load that's being formed by the A, the B, and the C circuits being powered by your voltage source. All right, and again, it's the job of field-oriented control and power electronics to deliver those voltages. All right, so let's copy this. All right, and again, this is what we just ran, which is a constant, or it's going to be a constant inertia shaft, and our robot's way more complicated than that. So let's get back to our robot model. Not there. All right, and so 3-phase motors take a little bit longer to run, so I'm only going to do one of them, but I will choose my critical axis. right? And so let me see if I can do this very well. So I want to, and you'll see that not only do I match kind of the voltage connections, the shaft, and even the positions on these things, but the user interface is as close as it can be. So here's the hard part. I want to get both of these open at the same time. So let's go here. And I think, nope, that one. All right. Okay, and so 10 volts. And then we went just keeping it simple, 10, 10. Yeah. Inductance is really, it's a lot like mass. It's going to essentially kind of define how rapidly the system can transition. And again, it's delivered really through the catalogs as you select motors using the motor catalogs of your motor vendors. Right? And that I'd say that kind of a key thing that's different with PMSMs is that they have this thing called pole pairs, but typically it's 4 pole pairs. And so we'll select that, cancel that, and these are essentially, I'd say, good replacements. That they're equivalently parameterized, right? Although fundamentally they're very different. A brushed DC motor is very different from a PMSM. Right, but with our matched user interfaces, I think we got it. I'm going to do one little check and make sure that, yes, we're now running at 10 volts. And so let's click on OK, and let's hit run. And it runs a little bit slower with the AC motor, but it's harder calculation. Okay, so that didn't take too long. Right? So again, I'll play it back at 4x speed, and you'll see it moves through that trajectory quite well. Right? And here comes the return up, and it does it without a problem. Right? So there's your other solution, which is switch the motors. Now, in this example, we just switched the motor associated with that forearm, and I went ahead and I added a measurement because I think right here that I should put, oh, I do have both. Let's see, scope, like that. And let's hit that like that. So here's the voltage, here's the current. No longer do we have these, nice harmonic oscillations for each of our voltages. And that's because, mechanically what we're doing is much more sophisticated, right? And so we're essentially, if you think about torque being proportional to current, well, these currents essentially represent the different torques required to do the different maneuvers, and these are the voltages that will drive that. I think I'll kind of wrap up just kind of showing where we're going to go with this, right? And in a way you kind of see it here. Let's see, let's get back here. So we got our controller, our mechanics, and our motion control, right? So it's interesting, why are all these things kind of highlighting the way they are? And let's go to controller and mechanics, right? So we expect this, basically, I think if I go visibility, show only this, there's the robot mechanics expressed with SimScape multi-body and what we call mechanics and electronics. Right? So now let's kind of show that on the controller, we have this too. Let's show only this, right? And maybe it's a good idea to have them both open. So show this, all right? And then finally, turns even our motion command has a robot. This one happens to be hunched over. Let's show it like that. And I wish I had that great plate back up there, but can I get that quickly? Yes, it's called motion. Show this. All right, and we'll kind of get into it. These will be included in the videos that we'll do, but the basic idea is we generally know how we want the end effector to move. That's essentially what the gray plate's doing, but we need to figure out what are each motors of this assembly doing. And then essentially through our mechanical model, we'll get our inverse kinematics for free. And I want to kind of show what we're doing on the controller side. So, we've already talked about the controller has its own robot. Let's go to control algorithm. So go to the block. All right, so this is our control algorithm. All right, and you'll see here that here's your inverse dynamics, but it's that same mechanical model based on the same, bodies or solids or parts, whatever you want to call them, that make up the assembly. All right, here it happens to be one of the parts. Here it's mass, inertia, all that kind of stuff's defined. Okay, but instead of telling it the torques we want, that's what a good controller is going to do when we implement that torque through our power electronics and our motors, we're telling it how we want it to move. This is coming from our inverse kinematics provided by that hunched over robot. And what's cool about that is it generates what we're calling FF here. And here really is kind of the control algorithm, and FF stands for feed forward. It means that we can calculate and estimate a torque really well, and that's going to help the PD, I'll call it the feedback controller. We're going to do some interesting stuff with this. But one of the things that we're going to kind of get into is that you can save a lot of money if you do this sort of stuff quite well. And as we get into implementation, we'll choose a sample time. And the sample time that we got to work, I don't know if you'll be able to see this very well, but we got to run at 100 hertz, right? And I'll just say it's a completely different game on control, or let's say, hardware implementation when you're running at 100 hertz versus like 10,000 or maybe even 100,000, which usually requires like a FPGA or some much more expensive workflow to design that. So anyways, we're going to get into a lot of great topics on this series, and looking forward to I'll just post these videos and hear what you think. Thanks for watching.